I call this talk the curious case of computational shortcuts and hardware choices. I'm actually going to focus more on hardware choices, but this is work in collaboration with some students of mine, Sashwat and Kwong here at University of Virginia, as well as students from the Cohere for AI Initiative, Harsha and Nishrant, and collaborator Marco from NYU and Sarah from Cohere for AI. It's now getting a lot of interest, so because machine learning has become really instrumental in assisting us for many decisions and I would say even policy operations which are involving individuals. So you can imagine this has been used for assisting in legal decisions, in determining whether individuals qualify for given benefits such as loans, as well as assigning resources to entities of individuals. So those are just a few examples, but as data-driven systems become more and more pervasive, then they also introduce new risks that necessitates new understanding. And so fairness is a key concern. It relates to how those systems handle discrimination and where the biases come from. And so this is a key concern not only for technologists and for researchers, but it's part of a wider pressing issues. In fact, just a few months ago, President Biden signed an executive order to advance the racial equity in federal government. And this is part of a larger agenda, which led to the draft of the Bill of Rights by this administration, which imposes some equity obligations for AI systems that are developed and adopted by the government. Even more recently, just a few days ago, this report from the presidents came out. So this is about how to use AI, how to harness the power of AI for scientific and engineering challenges. And there is a whole section in there talking about how to adopt principle of responsible, transparent, and trustworthy AI through all the stages of the scientific research process. And so to me, there's really like the main catalyzers that have driven the research of ML to applications that are this important are really these three factors: larger models. You see here we are seeing an illustration by publication dates on the x-axis and number of parameters in log scale on the y-axis. So we're seeing how those models have increased in size, and this spans across all domains of vision, language, and so on. The second is better compute. So we've seen a diversifications of powerful and different type of hardware and platforms, as well larger data sets. So and each of those three key factors leads to some challenges. So, for example, larger models leads to the challenges of how do we train those models efficiently. Better compute leads to the question of how do we choose the hardware over which training our model, and larger data sets leads to privacy issues. In this quest here, when we are looking at training those sophisticated models, we realize that machine learning models are rarely really deployed as is, but those models, while they are designed to kind of learn an hypothesis that best approximates the mapping from available data to data labels, the resulting models are deployed within some consideration in mind, right? They are deployed to satisfy some context-specific or application-specific restrictions. So, for example, due to model size or due to the resource constraint setting, one might adopt pruning techniques to scale down over-parameterized models, or due to policy requirements, one might adopt privacy-preserving techniques to modify the inputs of the outputs of those models, so to remove certain privacy-enhancing information, as well as we are often using ML services to train those models rather than training them locally. We're training now those models on clouds, and so thus we're losing the ability of really control the kind of hardware and specific setting that we would have had otherwise. And so our research has shown that in each of those parts of the pipeline here might contribute to the exacerbation of disparities. So as we've shown in a paper in a RIPS 22, network pruning, which is a compression techniques that it essentially removes network weights which have low impact to the model accuracy. So these techniques scales down over-parameterized models, but we have shown that pruning also creates or exacerbates disparate impacts. We're showing here the accuracy across various groups in vision classification tasks, where white here represent the majority group and others represent a minority group. And we're seeing that as the amount of pruning increases, so as the amount of weights that we're removing increases, then this exacerbation of the disparity in accuracy increases. Similar observation that we had in the context of privacy inference. So privacy inference is a context in which we're performing privacy computations on encrypted. Well, we're performing training on encrypted data directly, and so this is an expensive process. So cryptographic computations are notoriously expensive when applied to nonlinear functions, and so people typically approximate nonlinear functions with surrogates, and in this case, they approximate linear activations, nonlinear activation functions with some linear surrogates. And here we show that as the number of these nonlinear activations that you are linearizing increases, then this also results in a larger fairness issues. So for instance, this group here representing the majority group shows almost no impact in terms of the number of linearized ReLUs that we're adopting, while this group here, which is the minority, shows large decrease in accuracy as we're increasing the number of ReLUs that we're linearizing. Finally, there has been limited work to date concerning the influence of hardware in the ML performance, but as we've shown in this recent work just accepted at ACML, there's the hardware selection may play a fundamental effect in amplifying the disparate impacts in performance. So in this figure here, we've shown the accuracy of a set of models actually, trained over different hardwares. And so the models remain the same. We're only changing the hardware. And we're showing that this can have vastly different performance results, especially for minority groups. So here we're showing, again, white is the majority group. And we're showing that the differences in accuracy across different models is somewhat limited, while on others, which is the minority group, we have a much larger variance in performance. And surprisingly, this effect here persists even in balanced data sets. This is obviously an important aspect because those models are used for important tasks, and so those biased effect can have downstream implications for individuals. As I said earlier, those are models that are used in many tasks, including criminal assessment, hiring, or lending. And so those observations now are becoming more apparent, but their causes are still largely understudied. And so this is the purpose of this talk then, is to shed some light on why those issues are arising, right? So this is the question, where are those issues coming from? So we're going to focus on the last example that I gave you. So this the hardware selection problem. But the theory that I will highlight will actually can be broadened and can be applied to any of the example that I made. So network pruning or private inference and so on. So here, this is the setting. So we're given a data set, and this data set, it's a classical data set. So we have a set of feature xi. We'll have some discriminant feature that allow us to identify from which protected group an individual comes from. We call it AI. And then we have some labels. And we want to train a model by using classical empirical risk minimization. We're using an ML service, or maybe we're selecting an hardware. So this model here then gets trained on one of M hardware training platforms. And we might get some different results based on the hardware platform that we're choosing. And so we want to understand the differences in those results in terms of fairness.
What kind of model in this case we're talking about? Is it like this popular transformer-based models, or it's I'm just wondering, is the type of model also plays a, has significance here?
So yeah, that's a good question. So all what I will discuss, it's agnostic to the type of model. And in fact, our experiments, while this particular paper here has not used language models, but we have recent works that also extend this to language models. In this type of work here, you most often notice ResNets or VGG, so mostly vision models.
It could be generalized to the transformer models.
Yes.
And what can you also please clarify, when you're talking about hardware training, like what kind of hardware we're talking about here?
So this is basically different GPUs and different GPUs families. In the results that you will see later on, we will use different families on NVIDIA GPUs from 100, A100, T4. So what is fairness for us? Fairness, we are going to analyze fairness based on this notion, which we call hardware sensitivity. So this is defined as the difference among the risk function of some protected group, A, of models trained on different hardwares, right? So we take a model, M, an hardware M as reference, and then this theta star M simply means that we have trained that model on that reference hardware M, right? We got those weights. We've trained it, and we're assessing the accuracy of that model for a particular subgroup. So this is the subset of the data samples that belong to that particular subgroup. And we're comparing this notion here, this performance notion, with the performance that is attained on a model trained on a different hardware, right? Everything else they fixed. The only thing that we're changing is the hardware, right? All other randomness sources are controlled. And the notion of fairness violation that we would like to minimize is this maximal hardware loss difference across different groups, right? So when you look at the group white and the group others, we would like to equalize this kind of disparity of variances that we are seeing across different hardware. So let's jump into the main result here. Why hardware tooling induces unfairness? And so in this work here, we provided an upper bound on the hardware sensitivity. So once again, hardware sensitivity here reflects to the variation in performance just because we're changing the hardware, right, for a particular group. And this bound here is important because it allows us to isolate some key components then we're going to use to explain the reasons why we have this observed unfairness. And so firstly, let's just notice that there is this coefficient here, which we're using in each of those expressions. This coefficient rho denotes the largest differences of the model's parameters between a model and a reference model. So this is nothing else than you take a model, you training over an hardware M prime, right? And you get their model parameters. And then you take the same model, you train it over a different hardware, and then you expect to have the same model parameters if you do exactly the same operations on that different hardware, but actually we compute the differences across those two model weights, and the model weights is never zero. So there is some differences in parameters, and this is important. I mean, it's important that this aspect is non-zero so that this bound here would actually work. The two key factors that are regulating unfairness that are arising these bounds are the group gradient flows. So those are the gradients values from the samples from a particular group. They informally relate to the local optimality within that group. The gradients flows for the majority groups are small. The gradients flow for the minority group instead are larger. And so small numbers here, since we're multiplying this number by the rest of the coefficients, means that we have a smaller upper bound on unfairness, right? So the small number here will denote typically more fair results. The second component that we have here is the Hessian of the loss function associated with the group A. So, and where this lambda here is the maximum value. So this component here informally denotes the local curvature of the loss surface, right? So larger in value of the Hessian will denote sharper curvature than smaller ones. And so as we can see experimentally that once again, majority groups here, white, I'm not sure if you're seeing my pointer, the majority group white here has smaller in values than the minority group. And once again, this factor here, since it's a factor that we're multiplying by other constants, implies that we're having a smaller bound, right? So more fair results for this white subgroup here. This bound, though, should tell you something, right, about why this is happening. So there are really those two components that are foundational in this aspect here. Let's dive a little bit further. This result here basically shows that the unfairness in hardware selection lies in the differences of the gradient flows and the Hessian value. So in terms of the first issue, so gradient flows, we took a look at property of the training data. And so in particular, we look at the size of the training subgroups, and this is obviously playing an important role. So in particular, this result here shows us that if we have two groups with different training sizes, so group A has more samples than group B, then a convergence, the gradients for group A are going to be smaller than the gradients of group B. And so we can notice this experimentally on this nonlinear model here. So once again, white is the majority group, so it has 5 times the number of samples than the other subgroup here. And as I showed you earlier, we're seeing large differences in the gradient flows. So the gradients flow associated to the white subgroups are much smaller than those associated with the other subgroups. And this is reflected with the hardware sensitivity, right? So we have smaller accuracy differences in the various hardware sensitivities for the white subgroup than we had it on the other subgroup. So this is an explainer of why smaller groups yield large gradient norms and consequentially amplify the sensitivity to stochasticity, which is introduced by hardware. The second key factor that we have presented is that of the Hessian function, right? The max AM value associated with the Hessian of the loss. And so intuitively here, the Hessian is an indicator for the shape of the loss function around a particular optimal solution, as well as for its generalization capability. So we're illustrating this concept here pictorially in this figure on the left. So we have a group A, which has a flattened Hessian, so meaning that the max AM value is small. And the group B, which has a larger max AM value, so we have a sharper Hessian. And so for a group, and then we are comparing a model in black trained on one hardware versus a model in green trained on a different hardware. And so we can notice that as we are basically reporting some differences in the model parameters, although there are some differences in these model parameters, this shift here does not really bring a lot of performance loss in terms of the group loss for this particular group here, but it does indeed bring more performance loss for this group, which has a sharper loss function. We show that this components of the max AM value of the group Hessian can be bounded by a component which captures the proximity of those data points to the decision boundary, and then a component which summarizes the error. And so this is an important observation. Intuitively, it shows us that the maximum value of the group specific Hessians are directly linked to how close those samples from the groups are to the decision boundary. And it's going to be important because we're going to exploit this concept. And we can see experimentally here that even in nonlinear models, when we have groups, minority groups like others in this figure on the bottom left, where we have short distances to the decision boundary, right? Those groups are corresponding to larger Hessians. So similar observations can also be made on other data sets. In the interest of time, I'm going to focus on some experiments that extend this kind of results. So the analysis that we have conducted used different hardware. So we use Tesla V100, Ampere A100, Tesla T4, and another L4. So those are different hardware choices with different system levels, but are also hardware that are adopted across various research and industry. And we look at different data sets, both balanced and unbalanced. We created an unbalanced version of CFAR by reducing the class ship to 20% of its original size, and then use UTK, phase, and Celebi as natural imbalanced data sets. Those are basically image data sets that are widely adopted in the fairness literature. And we use a variety of architectures and fixed all sorts of stochasticities. This includes fixing random seeds for our Python libraries, having constant data loading and augmentation properties, fixing initial model parameters and hyperparameters, as well as using full precision whenever feasible. Let's delve into the results. The takeaway is that in the experiments that we conducted across T4, V100, A100, and L4, we found notable fairness variations across groups. And so firstly, notice that the small hardware sensitivity also, so the fairer groups, also corresponds to the groups with the higher accuracy. And to gain a better understanding, so if you examine the sensitivity of the hardware sensitivity of the class ship that we are imbalancing, so in this particular plot here, the lighter green colors denotes the balanced version of that class, and the darker green color denote the unbalanced version of the data set. So here we're noticing a 57 increase in hardware sensitivity after imbalancing this data set, which also corresponds to a decrease in the class accuracy for that particular class. And as we established earlier, the magnitude of the gradient flow within a group is directly linked to the gradient sensitivity, and so there is a strong correlation between the group gradient flow and hardware sensitivity. We notice this in the CFAR 10. If we are observing the balanced version for the class sheep and the unbalanced version for the class sheep, we notice a 62% increase in the gradient norms, and this corresponds in 57% increase in hardware sensitivity. So you notice the correlation that exists there. Similarly, in UTK and Celebi, so in UTK datasets, the differences between the gradient norms between the majority and minority group is 95.2%. And so, as you noticed earlier, there is large differences in accuracy among those groups. The second factor that we looked at is distance to the decision boundary. So we related the max AN value of the group Hessian with the distance of to the decision boundary. We can observe how this distance to the boundary here relates to the hardware sensitivity in a couple of data sets. So here we're in a UTK data sets, we're showing that the minority group is 67% closer to the decision boundary than the majority group. And this corresponds to much higher variation, right, and of hardware sensitivity for that particular group. Similarly, in Celebi, the minority group, so blonde male, is 61% closer to the boundary than non-blonde female. And once again, this corresponds to much higher hardware sensitivity and variation of that hardware sensitivity for that particular group. So now that we have an understanding of the reasons for those variations, then we could try to have some mitigating solution. And so one possibility would be that of equalizing the factors that are affecting this notion of unfairness that we introduced, which are group flows and Hessians. And so how would you do that? You essentially augment your classical empirical risk function with a term which computes the differences between the group gradient flows and the population gradient flows, as well as you do the same with the Hessian functions. But this is really expensive. And so what we did in the paper, we use a surrogate. So, and as surrogate, we're using the distance to the decision boundary. And so this works fairly well. We noticed that when we're augmenting this component to as a penalizer, right, to our empirical risk function, we can get pretty substantial reduction in unfairness. So in UTK phase datasets, we get 66% reduction in unfairness. In CELEB, we get 38% reduction in unfairness, while leaving the accuracy, the overall accuracy of the task almost invariant. And so this is interesting because this kind of solution here, it's really agnostic to the type of hardware, right? So we can implement it on the training mechanism itself. And we have adopted this solution, a similar solution, also in other contexts, so like in private inference, as well as in pruning. So this solution has been effective in other contexts as well. So let me jump to conclusions. So we look at what I think it's an often understudied aspect or overlooked aspect of ML training, which is the choice of hardware. We show that variation in hardware can lead to disproportionate effects across different groups. And we presented a framework that quantitatively assesses the hardware-induced disparity and identified gradient flows and differences in the local loss surfaces as the primary contribution for such disparities. We have validated those findings over extensive empirical settings, including multiple hardware, platform, datasets, architectures. And those observations are important because the sensitivity of the model performance to specific hardware choices really, or the model simplification as well, can lead to unintended effects. So for example, think of an organization that releases their source code and the model parameters might tell you that you have satisfactory performance level for certain demographic groups, but the claim performance could be substantially lower if they are implemented on different hardware platform. So the hope here is that this can be taken as lesson learned and cautionary tales for us to implement more responsible AI training strategies across different settings.
Michael is asking, is the size of samples group the same as the batch size?
No, that's so the number of data points they're far larger than, maybe I have some data, I don't even know but I think that you can think CFAR I think has 10,000 data points. UTK phase and CELEB has 200,000 if I'm not mistaken, right? So they're far larger data sets than what the batch size can have.
Can you clarify if the models were both trained and tested on different hardwares?
The model were both trained and tested on the same hardware in all the results that you have seen. So the disparities that you're seeing are not actually arising because of training and test deviation in a sense, but there is, if you actually take that additional caveat into account, then the disparity can be even larger.
When you said the disparity can be larger, you mean when it is trained on a different hardware and tested on a different hardware?
That's right, yes.
Let's say when you want to balance the minority class, you simply repeat the data points in the minority class.
Oh, I see.
So the number of data points is the same. Does that make the training process more fair, or I assume not, but?
I think data balance is definitely a predominant factor in those unfairness results that we're observing, but it's not all, because as I showed here, the decision boundary plays a key role in this bound. And so we actually show that even in balanced data set, you can have performance disparities. So you can think that even if you're training a model over a balanced data set, for a reason or another, you may have some classes that are much harder to separate than other classes, right? So those data points are going to be closer to the decision boundary.
Maybe I misunderstood your presentation on the class balancing. Is it true from your experiments that when the class is balanced, the unfairness is slightly the fairness is slightly better than unbalanced? Or
so for unbalanced, typically it is for unbalanced cases. Typically, you will find more unfairness, right, for unbalanced cases.
Makes sense.
But this is a very specific case. The CFAR10 here, it's a very, very particular case in which unbalancing actually gives you a little bit more fairness. And it's a very, very peculiar case. Why? Because we are unbalancing the class that had the highest performance, right? And fairness here, it's measures as the difference between, the highest performance minus the lowest performance group, right? And so here, it just so happened that after unbalancing this, we're reducing the performance of the highest performing, right, of the highest performing class. And now the highest one will become this one, which is slightly lower, right? And so we get a little bit better fairness. That doesn't imply that this is a case that will happen all of the time. It's just a result of fabricating these unbalanced data sets.
And one last question: Do you have any spin-off work where you are also incorporating maybe properties of the hardware into account, like maybe?
Yes. That is a great question. So firstly, let me mention that I am not the hardware expert in this group that essentially worked on this paper, but we did have extensive discussion. There are certain aspects that can be really thought out and incorporated. So, for example, if you have hardware that accept different precisions, then those kind of considerations can be akin to the kind of considerations that we're doing when we do pruning or quantization level interventions, right, in the model. So we can use similar techniques that we're using in those concepts. But there are other aspects that are really beyond my expertise, including threadings and so on. And we don't really have a solution in mind for how to resolve such kind of problems. And this is the reason why it is neat to think about solutions that are software based, right? So they deal with the training itself and don't extend to the hardware.
I'm just wondering how the usage of synthetic data and the consistently increasing the scale of models can impact on fairness.
Researchers, so I'm aware of a couple of work that do indeed study the impact of synthetic data generation on biases of models. So there's a paper from Nicholas Packernot's group from UToronto. They did look at this ability of the model of processing synthetic data and then generating synthetic data out of this processing, and then showing that the model tend to forget the tails of these distributions, right? And we typically find those marginalized groups at the tails of the distribution. So I have strong reasons to believe that this process here might exacerbate the unfairness of those results.
Privacy setting trainings, there also could be, lots of biases. But let's say in healthcare, right, like they're like very sensitive domains where the privacy is important. So how to find that balance that it's still like privacy preserving training, but minimizes the risk of unfairness?
Yes, so this is a question that is very close to my heart And I cannot claim I have a full response to that, but we have done quite extensive research at the intersection of privacy and fairness, specifically at the intersection of differential privacy and fairness. So I can tell you from our experience in especially in decision-making processes. So what we have, some settings that we have studied were a setting in which you have a data set. You render this data set privacy preserving through a differentially private pipeline, aka census data. Data is released through some differential privacy considerations, and this data then is used to allocate resources to institutions and individuals. There's several trillion dollars that are allocated. Well, there's $1.5 trillion budget that is allocated essentially with such kind of data. So if unfairness arises in this kind of processes here, there is huge impacts in terms of societal and economic aspects. And so over there, one key result that we have is that the downstream process, the downstream function itself, might exacerbate the bias, regardless of how this noisy process is. So even if the noise that you're adding onto this data is unbiased, then if the allocation is a nonlinear transform, then you can imagine that regions over these allocation functions that have steeper local curvature magnifying the variance of the errors, while regions in which you have flatter curves, they will not magnify the variance that much. And so this issue is really, really, at the core of any kind of decision process. And over there, I think that there is a huge need to better understand those kind of impacts and better designing mitigation protocols.